Thanks for the introduction. So first, I would like to thank for my colleagues and funding source. So in recent years, we saw the proliferation of nonlinear algorithms in the field of medical imaging, and particularly for computed tomography. For example, we have model-based iterative reconstruction and deep learning denoising algorithms. These algorithms can be highly nonlinear and data dependent, thus posing challenges to image quality assessment. They can potentially result in non-intuitive feature enhancement or suppression, and the traditional image quality measures like impulse response may be inadequate for assessment. So let's take a look at some simple examples. At the top, we pass an artificial speculated lesion through either linear or nonlinear system. For a linear system, we can see that the speculated feature gets gradually disappeared while leave us with blurry edges. And for nonlinear system, those speculated features get almost completely removed, but still give us nice edge response. Also at the bottom, there is a Stayman denoising example where the impulse response may not be well defined. In this work, we would like to develop methods to characterize general nonlinear algorithms. As we know, local linearization is a classic approach which has been applied to the analysis of some classes of MBIR algorithms. And here, we would like to investigate whether a similar approach can be applied to analysis of deep learning algorithms as well. So we know that a large number of neural networks bear similar structure. The linear layers followed by nonlinear activation function, which is the only source of nonlinearity in such kind of neural network. A popular choice for this nonlinear activation function is called rectified linear unit, ReLU, which has state off if the input is smaller than 0 and state on otherwise. So the piecewise linearity of this ReLU will result in piecewise linearity of the entire neural network. And this kind of neural network is exemplified by the convolutional neural network, recurrent network, feed-forward network, etc. So for a given network, given trained network, any given input will trigger a certain combination of activation states of all ReLUs, which is defined as an activation pattern. An activation pattern defines a local linear system. For all inputs that trigger the same activation pattern, they will fall within the same local linear region within the input space. And within that local linear region, we can apply all the familiar linear system analysis tools, which were tools where we can, for example, we compute the Jacobian, which governs the signal and noise transfer properties. So we can leverage the piecewise linear nature of such kind of neural network to characterize their behavior. So in this, throughout this talk, we just choose an example neural network which has been successfully applied to denoise CT images. So we choose RedCNN, which is trained with 2,900 FPP reconstruction of thorax CT from the LADC dataset under a scenario of quarter dose reduction. So for this particular RedCNN, the total number of ReLUs is around 2.5 times 10 to the 8. So there will be potentially a large number of possible locally linear regions. So in order to map out the input space we care about and locate these possible locally linear regions, we need to start with choosing the operating point in that input space. So we would like to choose an operating point which has clinical relevance. And since we're looking at long images, it's reasonable to construct an example operating point which emulates long nodule. So we do this by adding a uniform spherical lesion of certain contrast and size to the uniform background, which we call an operating point mu0. And we'll add small perturbations to this operating point and see if the activation pattern change. So there are many possible perturbations we can add to this operating point. We illustrate our idea by choosing an example perturbation, which is the lesion contrast. And we use this as a search direction. By increasing it, and we investigate the extent of the possible local linear region. So note that here, we're looking at noiseless input to the network. For linear systems, the system response can be computed by using noiseless or the mean inputs. However, for nonlinear systems, this kind of local linearity does not hold anymore. Just For this network, particular network we're using, the RedCNN, we have validated that this local linearity holds for noise magnitude and correlation one can expect for this particular operating point. So we systematically increase the lesion contrast by a very small step size, and we plot out the cumulative number of activation patterns recorded by the system, which is on the y-axis. The number starts from 1 because the operating point itself define an activation pattern. For the first 3 steps, the activation pattern remains the same, which means all these 4 inputs fall within the same local linear region. And we visualize the Jacobian by extracting 3 rows corresponding to different locations within the ROI, which is location 1, 2, and 3. We reshape these rows into the size of the ROI and visualize this, these are called local kernels, and we visualize the central slice of these local kernels. So as you can see here, we can observe that the system is local linear but shift variant. So we keep increasing the lesion contrast, and we can identify 2 additional different activation patterns, and their associated local kernels are shown below. So the activation pattern is highly sensitive to small signal perturbations. However, the Jacobian with different activation pattern can be highly similar to each other. We keep increasing the lesion contrast all the way up to 0.04, and now we have seen that the total number of activation patterns recorded by a system is almost 50,000. So in addition, we investigate another region with higher lesion contrast and also plot the local kernels and visualize the local kernels. So notice that within each region of different lesion contrast, local kernels at the vicinity of that operating point appear very similar to each other, but if we compare across them, they appear differently. For example, we can focus on this the magnitude of these local kernels. So based on all these observations, we can see that activation pattern is highly sensitive to small signal perturbation, but the Jacobian can be similar even with different activation pattern. So therefore, we can form an approximate local linear region which may span multiple activation patterns. So in other words, the signal transfer property characterized by an operating point in mu0 can hold even for some perturbed input from this operating point, which trigger a different activation pattern. There are many different ways of assessing the goodness of such local linear approximation. And here, we choose to take the difference between the CNN empirical measure of any perturbed input mu k, take the difference with respect to its local linear approximation with respect to the operating point mu0. Then we normalize it by using the lesion contrast and obtain a normalized percent error map. We choose the maximum absolute percent error in this map, use it as a metric for assess the goodness of local linear approximation. If this max percent error fall below a certain threshold, then we consider it's good. Otherwise, it means it's stepping into another local linear region. So with the same range of signal perturbation, now we plot out the maximum percent error for all the perturbed inputs around this operating point. And if we use the 10% error as a threshold on the local linear approximation, then we can see that all the perturbed input around this operating point will fall into a single linear region. And we validate the local linear approximation for 4 test cases. We can lower this threshold to 5%, but now for all the perturbed inputs with lesion contrast larger than 0.01 for this part, they will step into another local linear region. And we locate this new region by choosing an operating point at where exactly the old local, good local linear approximation with respect to this old operating point starts to break down. So it's just at here. So now we plot out the maximum percent error for all the perturbed inputs with respect to this new operating point. And we successfully brought down the local linear approximation error for the first two test cases. So we follow the same idea and keep searching along the direction of increasing lesion contrast. And we can add another local linear region so that now we can effectively lower the local linear approximation error for all perturbed inputs below this threshold. The key point here is, remember, for the same range of signal perturbation, the system records almost 50,000 different activation patterns. But now, in either case, we can brought down the total number of local linear region to just a few. So this will make the analysis and characterization of nonlinear algorithm of this kind of neural network much more tractable. So bear in mind that we're dealing with input space with high dimensional input space, and there are many other possible perturbations which we can add to this operating point. And we'll illustrate this idea by choosing another example perturbation, which is the background intensity. And we would like to apply the similar idea to partition along this 2D search direction. So we generate 4 operating points, 1, 2, 3, 4, by using either the lowest or highest lesion contrast and background intensity. And then we generate 5 other testing points with intermediate lesion contrast and background value, so that we divide the subspace into 4 quadrants. And we first start looking at the upper left quadrant and check the local linear approximation error for testing point 1, 0, 4 with respect to operating point 2. If there are good linear approximation, then we continue to randomly sample some test cases within this quadrant. If all of their local linear approximation error fall within a certain threshold, then we can say that this region can be characterized, this local linear region can be characterized by this operating point 2. But if the random test gets failed, we need to iteratively go through this process until we fully partition this subspace. So we visualize some results by partitioning along the 2D results search directions. So we can use different threshold on that approximation error again, and first come up with the 10%. The lesion contrast range from 0.01 to 0.04, and background intensity from 0.02 to 0.04. We can visualize all the local linear regions, like there are yellow contours surrounded each operating point in this subspace. And similarly, we can visualize the partitioning results for 5%, and we obtain a finer partitioning along the 2D search direction. So this approach can be extended to even more search directions based on clinical relevant features, such as lesion size, shape, texture, etc. And so far, we have picked a search direction based on what we perceive to be clinical relevant. For example, the lesion contrast and background intensity. But there are many other possible perturbations we can go along, and there still leave a large space of possible search directions we care about. So we're wondering if there is a more directed approach to find a search direction or perturbation that of interest. So starting from this operating point, we can go along multiple search direction or adding multiple perturbation to it. Some of them will lead us to diagnostically important stimuli, and some of them to unimportant stimuli. Among these stimuli, so we would like some of them to get preserved in the system output with some clinical relevant features, for example, the lesion speculation and necrotic core, etc. But for some of them, we would like them to get heavily attenuated. For example, the stimuli with noise. we're particularly interested in one thing. Are there any search directions that has clinical relevant that are critical relevant, but are cannot be represented accurately by the system? The Jacobian of the local linear system could potentially tells us some information about this. This is analogous to the linear and shift invariant system, where the MTF tells us the certain frequency components cannot get through. And here, for example, we can perform the as singular value decomposition to the Jacobian, where we obtain the singular values, which can be viewed as the modulation for the singular basis. If a certain singular value is close or equal to 0, then the features corresponding to associated singular vector cannot be represented accurately by the system. If multiple singular values are close or equal to 0, then the corresponding singular basis can be viewed to approximately form a local null space. Any feature that's a local that is a linear combination of all these singular bases are considered to be a search direction in the null space, and they cannot be represented faithfully by the system. Enlightened by the SVD analysis of the local linear region, we can go through the following steps to construct a search direction we care about. We'll first take an operating point mu0 and compute a Jacobian and perform an SVD on the Jacobian. And then we identify a threshold epsilon on singular values and form a linear search direction by projecting clinical relevant perturbation onto singular vectors with the epsilon. So for example, we can simulate a speculated lesion mu k based on patient data from ID's data set, take the difference with operating point mu0 and obtain the shape perturbation delta mu, and then decompose into unpassed feature and passed feature. This unpassed feature will be then scaled and added to the operating point to serve as search direction of interest that in this null space. So let's look at some concrete examples where we have two operating points. We have two example operating points with the same lesion contrast, but with different background value. For the first operating point, we perform the linear search along the search direction with a scaling coefficient alpha ranging from 1 to 10, and we visualize the perturbed input and its salient empirical measure at different alphas. For the first cases, we can see that with increasing alpha, the salient empirical measure of the perturbed input start looking smooth, initially looks smooth, but gets increasingly speculated with increasing alpha. And the explanation that we step into different local linear regions and the unpassed feature no longer fall within the null space. And for the second case, you can see that the salient empirical measure of the perturbed input looks smooth throughout the range of alpha. And this is because the unpassed feature always fall within null space throughout alpha. So in summary, neural networks using piecewise linear activation or piecewise linear systems, and the transition between the activation pattern is highly sensitive to small signal perturbation. But we can use approximate linear regions and characterize neural network as tractable piecewise linear system. And the SVD on the Jacobian of this local linear region inform us search directions and help us identify features that are not faithfully represented by the network. In future, we would like to extend to more search directions for more comprehensive characterization of neural network. And thanks for attention.
Thank you. I think we can take a couple of questions.
Very nice talk. Maybe I can ask a question. So I was wondering because when you do low dose denoising, there are always noise. I know this analysis based on no noise analysis, right? So I want to wondering, have you looked at the divided linear region? How does those perturbation relative to the noise? So for example, like the noise will add perturbation to the image, right? So will that still in the linear region?
Oh, that's thank you. That's a great question. So actually we have looked at the noise cases. So, well, as we said, we have validated for the local linearity for the network under a certain noise magnitude and correlation one can expect for this operating point. And actually, by dividing the neural network into a traceable number of local linear regions, we can perform the prospective noise prediction based on their local linearity nature.
Okay, great, thanks.
One question I had was on how can you tie this to extend this to somehow understand adversarial robustness?
Adversarial robustness?
Yes, where also we look at small local perturbations, but you're kind of looking at activation patterns and such, but is there some connection you see?
Yeah, that's a good question. So I think our work could potentially shed some light on the guidance of constructing adversarial attack for and potentially improve the neural network robustness, because people there is a constant question of asking whether it's a more constructed approach for this kind of adversarial attack, which has bear some clinical relevant structure information, and hope this could have some use for that.
One question, aren't continuous functions approximable by piecewise linear functions generally?
So you're asking if we switch that activation function?
I mean, if you have a continuous function, generally, you can approximate it locally with a linear function.
Yeah. And
also, you rely on ReLU being used. That is not universal. Many people do not prefer ReLU. I mean, there are reasons to have something else. So what's inside the neural network usually should be left outside. You treat it as a black box.
Yeah.
And also neural networks are considered, I mean, there's a theorem that shows they are universal approximators. So you can approximate any function you can match the data with.
Yeah. So basically that you're asking that if we switch to some other activation function, which is not ReLU, and the neural network can hardly be.
I mean, you build your point here showing that ReLU is linear, but not anybody, I mean, not all neural networks use ReLU.
Yeah, thank you. That's a good question. So even we're not using ReLU anymore. But this idea of choosing the operating point and go search along a certain direction and to see the extent, investigate the extent of the potential possible local linear region is still a powerful idea. So it could potentially serve as an assessment tool. For example, if go along a certain direction, but even with a very small magnitude, the behavior of the network exhibits some erratic behavior, or the output changes dramatically, then we can say that, oh, this may not be a desirable feature for that kind of neural network.
Okay, thank you.
Let's thank the speaker again.